Welcome to Spring LIB.
We are told that these two half reactions take place within a galvanic cell, and in parts A through E, we are given different disturbances to the system, and we want to predict whether each one of these will increase, decrease, or have no effect on the cell potential. So we can begin by determining what the standard cell potential is in the overall cell reaction. Based on the fact that this is a galvanic cell, we know that the cell potential has to be positive. And so that means that the reaction with the greater standard reduction potential will undergo reduction, while the one with the smaller one, which is this half reaction involving copper in this case, will be reversed to undergo oxidation. So when we do that, we see that when we multiply the second reduction half reaction by 2, that 2 electrons are canceled out on either side, and the overall cell reaction becomes copper solid plus 2 Ag plus aqueous goes to 2 Ag solid plus Cu 2 plus aqueous. And the way that we set this up, the cell potential comes out to be a positive value because this is a galvanic cell, and that is 0.46 volts. And now we can determine what the reaction quotient Q is for this overall cell reaction, and that is a concentration of Cu 2 plus divided by the concentration of Ag plus squared. And now, in order to help us determine how the cell potential is affected by changing the concentrations of either one of these species, we can consider the Nernst equation, where the cell potential is equal to that standard cell potential, which is that constant value that we calculated of 0.46 volts, minus 0.0591 over N, which is a constant of 2 electrons that we canceled out on either side, times the log of Q, which is this expression that we just developed. So we can use that in order to determine how the cell potential is affected when we change the concentrations of either one of those species. So in part A, we are told that CuSO4 as a solid is added to the compartment containing copper. And so when we add CuSO4, that means we are introducing Cu2 plus ions as that solid dissolves. So we increase the concentration of Cu2 plus, which, based on that expression for Q, since it's in the numerator, will increase the value of Q. When we take the log of Q, it will then be a greater value than it was before, and we are subtracting that larger value from this constant value, and so the cell potential will ultimately decrease based on that mathematical relationship. So we know that the disturbance in part A will decrease the cell potential. In part B, we are told that we introduce NH3 aqueous to the copper compartment, and we are told that Cu2 plus reacts with NH3 to form CuNH3 2 So if we added a species that reacts with Cu2 plus, then the Cu2 plus concentration in the cell would decrease because it would be used to form CuNH3 2 So this time, the concentration of Cu2 plus ions decreases, which means that the value of Q decreases. As the value of Q decreases, so does the value of the log of Q. And so if that were to decrease to the point where it becomes negative, then we are subtracting a negative value and adding it, therefore, to the constant value of the standard cell potential, And so the cell potential would be greater than it was before. So when we decrease a concentration of Cu2 plus ions, we end up increasing the cell potential. And now in part C, we want to know what happens if we add solid NaCl to the compartment containing the silver electrode. We are told that Ag plus reacts with Cl to form AgCl. So similar to part B, we are removing Ag plus ions so that they can react with Cl minus ions. So we decrease the concentration of Ag plus ions, and that appears in the denominator in our expression for Q. And if we decrease the denominator, then that means it will lead to an increase in Q. And again, when we increase Q, we increase the log of Q, and we subtract a positive value so that when we plug it into the Nernst equation, the cell potential comes out to be a lower value than it was before we decrease the concentration of Ag plus ions. So therefore, this change would decrease the cell potential. And now in part D, we are told that water is added to both of the compartments of the cell so that the volume is doubled. So we have decreased the concentrations of both of the aqueous species involved in the Q expression by diluting it with water to the same extent where the volume has been doubled. But because this bottom term is squared, then if we decrease both of those concentrations, then due to the nature of the denominator and the reaction quotient expression, a lower value of the concentration of Ag plus resulting from an increase in the water that was added to dilute that and decrease the concentration of Ag plus, based on the fact that it is squared, will lead to an increase in Q because it is on the denominator and we decrease that concentration and that term is squared. So again, an increase in Q leads to an increase in the log of Q, so we subtract a more positive value from a constant value for the standard reduction potential, and that would lead to a lower value for the cell potential than we had before. So doubling the volume by diluting with water leads to a decrease in cell potential. And now finally, in part E, we are told that the silver electrode is replaced with a platinum electrode, and we want to know how this would affect the value of the cell potential. Well, the electrode does not appear in any form of our equation because platinum is a solid, so it does not factor into the reaction quotient Q because we cannot write solids in terms of concentrations. So it does not matter what type of electrode we are using, it will have no effect on the cell potential.